Yeah, so this is some joint work with Tarmo Uustalu, and it's about kind of models of computational effects, especially in the presence of grading. And I'll say something about grading in a few minutes, but let me give you some kind of motivation from kind of like the ungraded story of what I want to achieve. So the point is that there are algebraic structures that kind of appear when we talk about models of effects. So this is a thing that goes back to kind of Plotkin and Power. So there's this story by Moji about modeling computational effects using monads. And then there's something by Plotkin and Power about how we can kind of start with some algebraic structure and kind of canonically construct a monad from the algebraic structure, and then use that as a model for our effect. So an example would be, we might say, I have some language with non-determinism, which means I need a monad that somehow has some operations for interpreting non-determinism. And then I could say maybe, so I want some nullary operation and a binary operation, which should satisfy some equations. So maybe the equations of a monoid. And then somehow I want to canonically invent some monad, which has, which lets us interpret the kind of operations of a monoid. So now we want to do a similar kind of version of this story in the context of kind of graded computational effects. So I'll just give one example in this talk of how we might grade some programs. So here I'm grading by natural numbers. So here I'm kind of annotating my programs with some natural numbers, which I'm calling D and E in some places. And you can think of this as kind of an upper bound on the number of things that, that the computation will choose between. So we have non-determinism, we can choose between multiple options. And these grades are going to provide an upper bound on the number of things we can choose between. This is a somewhat artificial example, but it's sort of easy to understand. So that's why I'm using it here. And we have some others. So we might say, for example, I have a computation that chooses between at most D1 things and another one that chooses between at most D2 things. And then I get a computation that chooses between at most D1 plus D2 things by kind of non-deterministically choosing between these two computations. And then we'll have a similar thing for nullary non-deterministic choice and also some kind of over-approximation of the grades. So here I say, if D is less than D prime, then I can also assign the grade D prime whenever I can assign the grade D. So these are really upper bounds. So there are a bunch of other examples of grading. I'm just going to use this one in this talk. So the real motivation for this work is to kind of develop a notion of presentation for graded monads. I'm not going to talk about presentations today. This is kind of what we do in our ICFP paper, which I'll talk about in a few days. But what I'm going to talk about today is the kind of sort of mathematical foundations of why this notion of presentation will work. So it's giving us a kind of nice mathematical footing on which to kind of talk about these things. Okay, so I'll say what what the ungraded story looks like in more detail. So firstly, we say, so I might want to do non-determinism. So we say I might want to think about monoids. So monoids will provide kind of some notion of like nullary and binary non-deterministic choice. So we'll say, I want some monad whose algebras, an algebra looks like this, turn out to be equivalently monoids. And then it turns out, if we consider the free algebras, which are kind of the sets of computations, so this is the kind of set of computations that return elements of X, then because these things are algebras, they will form monoids. So we get some kind of nullary and binary algebraic operation in the sense of Plotkin and Power. And we can use these operations to actually interpret non-determinism, to actually interpret the effect. And there's a similar story for kind of every kind of algebraic effect we'd want to consider. Okay. And it turns out there is such a monad, and there is exactly one such monad, in fact. It's just a standard list monad. So we say a computation is just a list of results. And the nullary choice is just the empty list. The binary choice is just concatenation of lists. And this is really the only monad that satisfies this, because it turns out that every monad is kind of completely determined by its algebras. So to know what a monad is, you just look at the algebras. And because I'm saying the algebras should be monoids, this will uniquely determine the monad. So now we can ask for a graded version of this story. So now I'll say, instead of having a set A, I'll have a family of sets A. So for every natural number, I'll have a set kind of AD. And this you can think of as like computations that choose between at most D things. And then I might say, I want a graded monad whose algebras turn out to be exactly graded monoids. So a graded monoid is just like a monoid, except now I kind of assign grades to the units and to the multiplication. So 0 and addition. Then I'll say, well, the free algebras will then be graded monoids, and then we'll get some kind of algebraic operation-like thing, which we can use to interpret non-determinism. So to interpret the programs that I kind of had on 2 slides ago. The problem is there is actually no graded monad that satisfies this. So there is no graded monad at all, it turns out, whose algebras are graded monoids. This just doesn't exist. So we can't really do exactly the same story as like Plotkin and Power do. So I should say at this point what a graded monad is. So these you should think of as looking a bit like monads, except now we're grading computations. So firstly, for every set X of results, we have a graded set of computations, by which I mean we have a family of sets indexed by natural numbers. So we can talk about, so TXD will be the set of computations which have grade D. So choose between at most D things, for example. And then there's some unit and some Clausius extension or bind operator, which we kind of assign the appropriate grades to. So an example of this is there is a kind of graded list monad where we take the ordinary list monad and we grade the computations by saying, well, the computations of grade E should be the list of length at most E. So really the computations that choose between at most E different things. Okay, so this graded monad has some algebras. I won't say this in any detail, but the algebras of this thing are not graded monoids. So this is really different to the kind of ungraded story. And in fact, the algebras of this thing really don't have a simple description as far as I can tell. They're really just some kind of complicated structure that in a sense, I really don't understand. So these do not form graded monoids, but it turns out the free algebras of this thing do form graded monoids. So these graded sets of computations, each of them does form a graded monoid. So we can still use the empty list and concatenation of lists, and this will give us the structure of a graded monoid. So even though general algebras are not graded monoids, the free algebras are. And this, in fact, is really enough to interpret non-determinism. We only really need the free algebras to be graded monoids to interpret this. But when it comes to talking about presentations and things like this, we really want some. We really want to know more about this graded monad. So the thing that I'm going to prove a bit later, or the thing that I'll kind of explain later, is that this graded monad is in a sense canonical. And so when we start with the notion of graded monoid, this notion of graded monad kind of arises in a canonical way, which says something like the algebras of this graded monad, even though they aren't graded monoids in general, they are in some sense as close as we can possibly get. Okay, so I should talk about, I should say a bit more about what kind of graded algebraic structures I'm considering, what they should look like. So firstly, this is really the full definition of graded sets. We have a family of sets, and then some kind of coercion functions, which say we can over-approximate the grades. So we can go from A of D to A of D prime whenever D is less than D prime. And there's some notion of map between graded sets. So we can just say a map from A to B is a family of functions. So we can go from AD to BD for every natural number D. And this should be natural in D in some way. And then we can do something with graded monoids. We can say what a graded monoid is. So this is the full definition. And we can say a map between graded monoids is a map between graded sets, preserving the unit and the multiplication. And then we can organize these things into categories and we get some forgetful functor. This is really not enough structure to talk about these graded algebraic, these kind of graded algebraic structures. So in fact, if I had just considered like ordinary categories of graded monoids, for example, the stuff that I will say in a few minutes would just all be false. So we're really kind of missing something here. So the thing that we're actually missing is that there is a more general notion of map between these things. So if E is a grade, we can say a map from A to B of grade E is something that looks like this. So it's something that takes things of grade D to things of grade D times E. So we can kind of multiply the grade by some constant. And then we get appropriate notions of morphism of grade E for both graded sets and graded monoids. So in fact, these structures don't just form ordinary categories anymore, they form locally graded categories. So what this means is essentially you have a collection of objects, so for example, graded morphisms and graded monoids. And then we have graded sets of morphisms. So we can talk about morphisms from X to Y of grade E. And then we'll have some identities of grade 1, some composition which kind of multiplies the grades, and then satisfy kind of sensible laws. So graded sets, graded monoids, and kind of any graded algebraic structure you might want to write down would form a locally graded category in this sense. And this is really the sort of structure that we have to consider in order to kind of reason about these things. Okay, so in general, a graded algebraic structure will form some locally graded category which forgets into graded sets. So this will just send, for example, a graded monoid to its carrier, to its underlying graded set, and every morphism of grade E to itself. So it sends morphisms of grade E to morphisms of grade E. Okay, now the next thing I need to say is how graded monads fit into this picture. So this is where I want to mention relative monads. So I think Max already said what a relative monad is, and this is really the same kind of notion of relative monad, but here for locally graded categories. So these are kind of like monads, except they're essentially defined on only. So if you think of J as just picking out some collection of objects of C, these things are like monads, except only defined on some of the objects of C, so not defined on every object of C. But otherwise, they have some units, some class extension, which are analogous to the ordinary units and class extension of a monad. Here I have to say something about the grades. So I'm saying the unit has grade 1, and the class extension kind of preserves the grades of the morphisms. So all of these things behave very nicely, and we can do all kinds of nice constructions with them. The only one I want to mention is that if T is a relative monad, we have some notion of algebra. I won't actually give the definition, but there's some nice notion of algebra. And we get some forgetful functor, which goes into this category C. And also a free functor, which says for every object of J, I get some free algebra, some free T algebra. And these satisfy lots of nice properties, kind of analogous to things that you can prove about monads. So now I want to say that graded monads are actually relative monads for a particular functor J. So I can pick out a bunch of the graded sets. So I can say for every graded set, for every ordinary set X, I get some graded set K of X, essentially by saying I want the elements of X to have grade 1 and kind of freely constructing a graded set that satisfies this. And this will form kind of some locally graded category. I won't give the definition of morphisms, but this is some locally graded category that kind of embeds in graded sets via some functor K. Then we can expand out the definition of K relative monad. It looks like this. And it turns out this is really the same as a graded monad. So the unit and class extension look slightly different, but there's some kind of property of these graded sets K of X, which kind of lets us replace, well, a map from K of X to T of X of grade 1 is actually the same thing as a map from X to TX1, for example. So it turns out we have some nice formulation of graded monads in this setting. Okay, so let me go back to kind of what we were trying to prove. So I mentioned before that there's no graded monoid, there's no graded monad, no graded monad T, whose algebras are exactly graded monoids. By which I mean there can never be an isomorphism that commutes with the forgetful functors like this. But this list graded monad is actually canonical in some sense. So in fact, for every graded monoid, we get an algebra for this list graded monad. So there is some functor R, which commutes with these forgetful functors. And in fact, this is really canonical in some sense, in the sense that I'll mention in a couple of minutes. So to say what this, to say what this looks like, first I need to give you a more kind of another definition, another kind of monad-like thing. So this is a notion of flexibly graded monad. You should think of this as being more general than graded monads. It's in fact not quite more general in any precise sense, but it's in some sense every kind of structure that you can capture with a graded monad will be captured by a flexibly graded monad. So the difference here is that instead of saying I have a graded set T of X for every set X, I now have a graded set T of X for every graded set X. So now the results of my computations can themselves have grades. So the precise definition is, well, they are monads on this locally graded category of graded sets, or equivalently, they are identity relative monads. But I won't dwell on this very much. So an example would be, there is some flexibly graded monad of lists. We essentially say, well, if X is a graded set of results and D is a grade, I can say take list over X, where the total grades of the elements is at most D. The precise thing is here, but it's not so important for this talk. The thing that I really want to mention is that the algebras of this flexibly graded monad are exactly graded monoids. So there really is an isomorphism here. So this is something that we couldn't do with graded monads. And in fact, it seems to be some kind of general phenomenon that these algebraic structures cannot be captured exactly by graded monads, but they can be captured by flexibly graded monads. So this is really this is really the point of this definition. Now, as soon as we have a flexibly graded monad in this sense, we can actually construct a graded monad. So essentially, we just say, I can restrict T from graded sets to sets, essentially by composing with this functor K. So if X is an ordinary set, we get some graded set K of X, and then we can consider like computations with results drawn from K of X. And if we do this, this floor T will actually form a graded monad, essentially by restricting the structure of T. And this actually satisfies some universal property. So every algebra of the flexibly graded monad T is an algebra of the graded monad floor T in a canonical way, in such that, you know, if we can do this if we have any other graded monad T prime with a functor like this, then in fact there is exactly one way of mapping from T prime to floor of T, making some triangle commute. So in sum, this is really a precise sense in which I want to say the algebras of floor T are as close as we can possibly get to the algebras of T with a graded monad. And in fact, the second consequence of this definition is that the free floor T algebras are themselves free T algebras. And I'll say why this is important on the next slide. So I do have this, this flexibly graded monad of lists whose algebras are exactly graded monoids. So I can kind of take this universal property, construct some graded monad floor of T, and then I get some universal property that where I can actually replace T algebras with graded monoids. So replace this thing with graded monoids. And we get something that looks like this. So this construction of floor of T actually gives us this list graded monad that I showed a while ago. Together with some functor from graded monads to algebras of this thing. And now it actually follows that this list graded monad is canonical in some way. It actually satisfies some universal property. So in some sense, really, this list graded monad is as close as we can get to graded monoids. And in fact, it follows from this that we can't actually capture graded monoids exactly with a graded monad. The reason is, if we could, then it would turn out that R has to be an isomorphism, but we can just calculate what R does and see that it's really not. But then I also mentioned this thing about free algebras. So it follows from this also that the free algebras of this graded monad actually are now free graded monoids. So the free algebras of this list graded monad will form graded monoids in some canonical way. And this, in some sense, is the reason why we can interpret the operations of non-determinism using this graded monad. This is where, this is from where we can kind of construct these interpretations of the operations of non-determinism. Okay, so that's all I really wanted to say. We do have some other examples of this, not just graded monoids. In fact, there's some examples which kind of have this, where this same phenomenon kind of appears in our ICFP paper. But there's really two things that I wanted to mention. So firstly, graded monads don't capture algebraic structures in the same way that ordinary monads do. So for example, graded monoids are not captured by these things, but they do in some sense get close enough to actually get some story about interpreting kind of algebraic operations using graded monads. But the other thing I wanted to mention is that all of these results are kind of follow from some general stories about locally graded categories and relative monads and things like this. So actually, it seems that locally graded categories are really a good setting for kind of reasoning about grading in general. So we can really capture lots of stuff that goes on using locally graded categories. So actually, this talk is really about the stuff I talked about is kind of in a paper that we submitted to MPC. So a draft version of this is online, so you can look at this if you want. But I'll stop there. Thanks.